In this video, I'll be giving a brief overview of numbers, place values, and rounding. Starting off with numbers, you guys are likely familiar with a number line, which is just a way to represent a set of numbers. In this case, I'm going to be representing all the numbers that could possibly exist, and I'll show you what I mean by that. So I'm starting off with 0, and I'm adding some positive numbers to the right of 0. So just keep going onwards, and you can imagine that this extends all the way until positive infinity. So I have 0, 1, 2, 3, 4, 5. Now, all of the numbers that I just have listed right now, so from 0 all the way to infinity, all of these numbers are called whole numbers. And you probably are familiar with this term already, whole numbers. This just means that a number is whole. There's no decimal point, there's no fractional part. That's what we mean by a whole number. If I were to not include 0 and instead just start from 1 all the way to infinity as well, these numbers are called counting numbers. And like the name suggests, it's just the numbers that you would use to count something with. If I have some number of objects and I keep removing one object at a time until I reach the last object, what is the least amount of objects I will have? Only one. Assuming that I don't have none objects, I will always have at least one. That's why we start with 1 when we have counting numbers. Now, I have 0, I have my positive numbers. Let's complete this number line and add my negative numbers and assume this goes on all the way to negative infinity. Now, all of these numbers, 0, the positive numbers, the negative numbers, all of these together are called integers. And you likely will hear this term later on as you progress in math class, where we will start using the term integers to refer to some numbers. So right now, you know whole numbers, you know counting numbers, and you know integers. Let's stick with our whole numbers. So when we have, for example, let's use an arbitrary whole number, 45,321. Now, I know this is a whole number because, like I said, we don't have any decimal point, so we don't have any decimal part, and we don't have any fractional parts in this number. We instead just have a set of digits, and what we're going to do now is identify the place value of each of these digits. Starting with 1. Now, 1 conveniently is in our ones place. That's why I'm drawing a little O over it. Whenever we're identifying place value, by the way, we're going to start from right to left. You're not starting from 4, you're starting from 1 in this case, meaning the digit that's all the way at the rightmost side, at that end, at the right end, that's where you're going to start. So we have 1, which is in the ones place, and I'm going to write that here. Ones place, this is how you'd write it. 2 is in the tens place, so we have tens. 3 in the hundreds place, hundreds. 5 is in the thousands place, so TH, thousands. And then we have, in this case, 4 being in the 10,000s. So we have 10,000s place. These are our place values. And of course, if my number was larger, I would continue onwards until I reach the last digit on the leftmost side. In this case, I just have 45,000, right? But if I were to go onwards and onwards, I could reach millions, I could reach billions, and I would just keep going onwards with identifying the place value. Now, the reason place values are important is because we use them whenever we're doing any kinds of operations on these numbers. So for example, if I wanted to add two whole numbers, I would need to align them based on where their place values are. And I'll discuss this in detailed steps in another video. That's one example of where we'd need place values. Another example is if you want to just round. So if I have round 45,321, so the same number, to the nearest, let's start with 10,000s. So I want to round this to the nearest 10,000s place. And I'm just going to write it as 10,000s. So I have my number here, The way I would start this is first by identifying what place I'm even rounding to. So I know I'm in the 10,000s place. That's where I need to round to. So I go to that digit. 4 is in my 10,000s place. I'm just going to write TTH on top for 10,000s. Now, to be able to round to any type of digit, so any place value, I need to look at one digit to the right. So 4 is in the 10,000s place, which I'm trying to round to. I'm going to look at one digit to the right, which is 5. Now, whenever we want to determine whether to round up or round down, we will always compare this digit, meaning the digit to the right of the digit we're trying to round to, with the number 5. So over here I coincidentally have 5, but it could be any digit here that I would be comparing to see if it is greater than or equal to the number 5, or if it is less than 5. If it is greater than or equal to the number 5, that's what I have over here. This little symbol over here is saying greater than or equal to. If that is the case, then I will round upwards. So I will say round up. So in this case, let's see. Is 5 greater than 5? No. But is 5 equal than 5? Then yes, I know I will need to round up. But say I had a situation where this number right here was not 5 and it was a 2. 2 is less than 5. So in that situation, if something is less than 5, when I'm rounding, I would round down. And let's see what both of these circumstances mean. So let's start with the first one. So over here, we still have 5. 5 is equal to 5, so I know I need to round up. So what I'm going to do in this case, I'm going to go back to my 10,000s digit, because that's what I'm trying to round to. So I was at 5. I identified that 5 is equal to 5. Now I'm going back to 4, which is in the 10,000s place, the place value that I'm trying to round to. I will add 1 to 4 to round up. So 4 is increasing by 1. It's turning into a 5. And everything to the right will now become a 0. But now let's see what I have. I started off with 45,321. Now I have 50,000. This is me rounding upwards, right? Because my resulting value is greater than what I started with. So I rounded up. And I rounded up to the nearest 10,000s by starting off by looking at the 10,000s place, looking one digit to the right, comparing that digit with 5, seeing that it was equal to 5 so I could round up, going back to my digit, adding 1 to it to round up, and then I got my result. This is what we would do in this situation. Now, what if I instead said, let's round this same number, but let's round it to the nearest hundreds place. So it's the same situation, but now I'm going to be looking at a different digit. So I have 45,321. I'm looking at the hundreds place. So I have 3 in the hundreds place. I'm just putting an H to mark it. Now I'm going to look one digit to the right of my 3, of my digit in the hundreds place. So I have my hundreds place. Now I'm looking one digit to the right. And remember, we do that comparison. We see, is it greater than or equal to 5 so that I can round up? Or is it less than 5 so I can round down? I know that 2 is less than 5, so I must be rounding down. Now, I go back to my digit of 3. You might be thinking that, hey, when we rounded up, we added 1. So in this case, should we subtract 1 from 3? But no, when we are rounding down, what we do, of course, we're keeping the digits in the front the same. We don't have to change them at all. But the digit itself that we were rounding to, so the hundreds place, we will keep that digit actually the same. So 3 still stays at 3. And that's how I know, okay, I'm not rounding up, so I'm keeping it the same. And then everything to the right of 3 turns into zeros. Now, let's take a closer look. We started off with 45,321, and now we have 45,300. So that is how I am rounding down, because the number I got after rounding to the nearest hundreds place is a number that is smaller than my original number. But make sure you understand that distinction, that when we are rounding down, we are not subtracting anything from the digit that we were rounding to. So we were rounding to the nearest hundreds place. I had 3. I realized that the digit next to 3 is less than 5, so I have to round down. But when I'm rounding down, I'm not changing 3, which is in the hundreds place. I'm keeping 3 the same. I'm simply not adding anything to it, so I know I haven't rounded up. I've kept it the same, and then I'm turning everything to the right into zeros. Now, hopefully this makes sense in terms of rounding. But in what situation would we actually need to use rounding? Now, you might come across a situation where you're trying to do some quick calculations and you don't want to actually do the steps of adding each digit to the appropriate digit. And instead, you want to be able to do it in your head. You want to do some quick mental math. So you might see a problem that says this: estimate the sum of two numbers. So let's choose two arbitrary numbers, 2,549 and let's say 1,720. Okay, let's go with those two numbers. So I want to find the sum, and remember, sum means when I'm adding. So anything I'm adding, the resultant value will be called a sum. And I have two numbers here, which are my add-ins, meaning these are the numbers I will be adding. So I have 2,549, and I have 1,720. But over here, there's this clue word that tells me that I do not directly add: estimate. Whenever you see the word estimate, that means you are going to be making kind of like an educated guess. You are going to guess in an educated way what these numbers actually round to, so what they're really close to. Now, you might be wondering, hey, it doesn't really tell me what place value I have to round to. It's just telling me estimate. So do I round to the tens place? Do I round to the hundreds place? What about the thousands place? In a scenario like this, when it's telling you estimate the sum, you will always be rounding to the maximum possible value that your number has. So in this case, I have a ones place, I have a tens place, I have a hundreds place, I have a thousands place. Thousands is the highest value. I'm going to be rounding to the thousands. Same applies for both because we have the same place values for all. So let's round 2,549. I have 2 in my thousands place, and I know I'm rounding to the thousands. I'm going to look one digit to the right, 5. Is 5 greater than 5? No. Is 5 equal to 5? Yes. Because remember, the condition is if it's greater than or equal to. So it passes the condition, so I have to round up. So I go back to 2, which is in the thousands place, and I add 1 to it. The rest becomes zeros. So I've rounded it up. I got 3,000. Now, I'm going to do the same for 1,720. 1 is in the thousands place. I'm looking one digit to the right, which is a 7. 7 is greater than 5, so I'm rounding upwards. So I go back to 1, and I add 1 to 1. So I get 1 plus 1, 2, and everything else turns into zeros. Now, I have 3,000 and 2,000, and I was asked for the sum. Remember, sum means I have to add those numbers that I've been given. Now, I rounded those numbers because I was told to estimate, so I know that my sum for 3,000 plus 2,000 is 5,000. And I don't need to do any work for it because I can do this in my head. That's the power of estimating. That's the power of being able to round quickly instead of having to do all the work of adding all these digits one by one. So now, that's how you would solve this kind of problem. A lot of times, students get confused, and they will do this. They will take 2,549, they will take 1,720, so they take both the add-ins, and they will solve it individually. So they start 9 plus 0, 9, 4 plus 2, 6, 5 plus 7, 12. So they have 2 here, carry the 1, and then they will get 4,269. Then they realize, okay, I found the sum, but the question says estimate. Now, at this stage, they will try to round, and they'll see that, okay, 4 is in the thousands. I look one digit to the right. 2 is less than 5, so I round down, which means I keep 4 the same, and I add a bunch of zeros. This is wrong. You are essentially solving the entire problem, and then you are rounding the sum. That's not what the question is asking. The question wants you to estimate the sum, meaning even before adding regularly, you will round each addend. Do not do this. It will also give you the wrong answer. See, 4,000 does not match our correct answer of 5,000. Another thing to note, and I will probably conclude the video with this, is that 5,000 or any number, any whole number, has some commas here. So let's look over here. I know I put my comma right here. Over here, I put my comma right here. Over here, I put my comma right here. You might notice a pattern. When I have some large number, and I'm just going to write a bunch of digits together. If I just gave you a bunch of digits like this, and this is a random example, you would not really be able to tell how to read this unless I spaced it out nicely. That's why we have commas. Commas make it easier that as you get a bunch of digits, you're able to read it out easily and determine what place values those digits have. Now, it's not just we can put a comma anywhere. The placement of the commas matter. And you might notice the pattern that there seem to be 3 digits always. And that's exactly what it is. Moving from right to left, you will always place a comma at every 3 digits. So we have 1, 2, 3, comma. 1, 2, 3, comma. 1, 2, 3. And now we don't need to add a comma because there's nothing before the 6. So we know that this number would be written like this with commas. And now we can easily read it as, okay, this seems to be 676,543,621. You might come across a question where it asks you to put in the commas for some random set of digits. You might get 759217342. It's really simple. You're starting from right to left. So we have 1, 2, 3. Remember the rule, 3 digits, comma, 3 digits, comma. And then you have it, 759,217,342. All right? That's how you're going to place the commas, and that's what you should always do when you're adding or subtracting or really doing any operation with your whole numbers. Do not forget to place the commas. The commas make a big difference later on as you start getting and working with larger numbers.